So we're going to start right now the next session. Like I said, the next session is about women space engineers. We are very excited to have two amazing women connected here that are going to talk to us about what space engineers do, how their work is done in their labs. And before I go on talking nonstop, I will just introduce the speakers and let them do the rest of the job. So we have Sarah Rodriguez-Castillo and Yaquelin Rosas. Sarah works in the European Space Agency in the Netherlands. She's an astrophysicist and she's a materials engineer working in the materials physics and chemistry section in the European Space Agency. Her job is to support all the projects of the European Space Agency and all the technology programs in the frames of material suitability for each mission environment. The same material is not always suitable for two completely different missions. So her job is to do this, to support all the missions. And Yaquelin, she works in the German Aerospace Center in Berlin, Germany. She's an aerospace engineer. She's currently working as a project manager in Envision. There is a future mission to study Venus. She's also supporting the development of mechanical components for Janus, which is a camera that on board of the JUICE mission, which is going to be launched to Jupiter. So they're working in completely different projects and they're going to tell us more about their projects. So I let the floor to Yaquelin and to Sarah. Thank you very much for being here.
Shall I start then, or Yaquelin? Okay, I start then. Let me, because I'm new to this thing, let me share screen and I share the PowerPoint. So now you should see something. Voila. But then I don't know what you're saying. Aha. Yes.
It's good. It's good. We see everything.
Yeah, no, but then my PowerPoint presentation went on top of what I'm seeing that you're seeing. So then it's a mess. Yeah, so I'm going to talk a little bit about how it is to work as an engineer in ESA, in the European Space Agency. Of course, there are many types of engineers here in ESA or in life. Yeah, so I'm going to focus as my work as in my work as a materials and processes engineer. So I work in ESTEC, which is the European Space and Technology Center, and it's located in the Netherlands. I'm seeing this. So that's actually the corridor that I work on. Do you see my, no, now you see my mouse. So yeah, so my office is around here and my lab is here. This is taken from the door of my lab. And I pass by all these models of satellites and parts of propulsion systems every day, which is awesome. So here's me taking a selfie with an astronaut suit yesterday. I have, just before I go on, I have also created a couple of questions in Slido. So the number is 223344. So if you want to just start logging in so that then we can tackle them later. I think it's better now for you guys to get ready and to go choop, choop, rather than later like, So yeah, so what did I study? I had no clue. I had no clue what I wanted to study when I was in high school. I liked biology, I liked physics, I liked chemistry. So basically I always wanted to know why things happen. Finally, after a lot of thought and a lot of, yeah, but I'm really stubborn, I studied physics. So I studied physics in Madrid and I specialized in astrophysics where I learned about galaxies, planets, interstellar medium, intergalactic medium. So it was super cool. And then it was so cool that after some years, I ended up doing a PhD doctorate in the topic in Toulouse. But then in the meantime, after I studied physics, I was thinking, yeah, this is very nice, but it's very theoretical. So I still wanted to know more things. I wanted to see the applications of all this theoretical and basic knowledge that I had in my head. So I studied materials engineering. I went back home. I'm from Bilbao in Spain. So yeah, I studied there in the University of the Basque Country. And there I studied, well, from project management to, that's more like the engineering, basic engineering part that I think all engineers learn. But I focused, of course, on materials, which is ceramics, metals, plastics, and so on. So now I want to make you think a little bit of what's the difference. Of course, you should know some topics about what's the difference between ceramics and metals and plastics. So something that you can think of right now, I'm not seeing the question, so I don't know if something is commenting, but anyway. So something that you can think of right now is that a ceramic, for example, is what we use to cook. So basically, it keeps a lot of heat inside so that it transfers all this heat to the food. Metals also transfer heat, but they transfer it much faster. And plastics, they melt. If you put it on top of something warm, they melt. So that's one property. Another property, for example, is that metals, when you try to bend the metal, typically it's much more difficult than trying to bend the plastic, pure plastic, typically. Of course, there are exceptions because now we have advanced with so many materials, with nanomaterials and with composites, which is two types of materials having fun together, basically, and taking the best properties of both. So how do we apply it to a spacecraft, all this knowledge? So if we go to the Slido, I think now, oopsie, no doc yet. I think now I can stop sharing this and I can share. Voila. So if we go to Slido, I think we are here. Yes. Yeah. So this is the first time also that I'm using this. So if I'm using it wrong, I apologize. So first question. Which material do you think would be better to keep a satellite rigid? So of course, when you send the satellite to space, first it has to go through the, okay. First it has to go through the propulsion. So it has to leave Earth. So it has to withstand all the vibrations that I think Yaquelin will explain later. And then it has to keep the original structure when it's flying towards the moon, towards Jupiter, whatever you want. Because you cannot have, for example, a telescope, a very nice lens, perfect, you manufacture it like this, and then you heat it up, you apply some loads, and then the telescope does blah, and you see nothing. So it's a tricky question, actually. Yeah, I didn't put the correct answer because it's a tricky question. So I see that some people have said metals, foam or ceramics. Well, foam is not the correct answer. I'm guessing this is Nasia tricking, I'm not sure. But of course, a foam, when you apply a load, the foam how you say it in English? Modifies the structure, let's say. So, a foam is not the best thing to keep something rigid, right? If you put a foam between two rigid structures, then it's another thing, because the structure would be the one holding the weight, and then the foam can deform. Yes, deform. So a foam is not the best thing. Then we have ceramics and metals. It depends on the environment that it's gonna fly. If you're expecting a lot of heat, a metal would expand much more than a ceramic. So if you have a cube, let's say, of a metal, if you apply heat on it, it will expand. If the metal is the same metal, it will expand uniformly. It will keep the structure, but it will be much bigger, while a ceramic will keep the structure. So theoretically, out of these options, which are not the correct option because we use carbon fiber reinforced polymers mostly, it would be between ceramic and metal. A metal, if you coat it, if you protect it from the heat, it would be a metal. If you don't protect it from heat, it would be a ceramic. Next question. Why don't we use ceramics in the whole satellite then? Because the ceramic is so awesome. Why don't we use it in the whole satellite? So there are four options. Because it breaks easily, so it's brittle. Because it's too heavy, so it's too dense. So the weight per centimeter square is too high. Because it's ugly. Or because it's expensive. So let me do this for a bit. Again, not the correct answer here. Eh? Because it's ugly, yes. Yes, that's totally it. No, because we can paint them. So yeah, we have two options now here. It is expensive, but space, because we don't send so many satellites per year, the budget per satellite is not so bad. Depends, but let's say money is not a problem, like in Jurassic Park. Of course, we want to make sure that we do things within budget, but basically we don't send ceramics in space in big quantities because it's heavy. And every kilo that you put in space just to lift off, it's a lot of not only money, but trade-off that you have to do, because you can only lift, so a satellite has to be propulsed with a lot of propellant, basically, in order to break the Earth's gravity. So the more weight you put on top, the more propellant you need. And then the more propellant you need, the more weight you have. So you want to put things that are light, but structurally solid, let's say. So it's because it's heavy. It also breaks easily, it's also brittle. So you cannot apply it in all the parts of the spacecraft. But we treat things with a lot of care in ESA and in space business. So if something is brittle, we make sure that, okay, it will not break. But yeah, it's basically because it's heavy. And because it's heavy. And then finally, what is the main disadvantage for space of using a metallic material? So we have 4 options. That it's shiny, the capacity to transfer heat or cold very fast, that it can corrode, or that it's smooth. Typically, unless you treat them. So we're talking about disadvantages. Thank you. So basically, I think we have reached the maximum. Again, tricky question, because of course nothing is going to be easy here in space. The corrosion is a disadvantage, of course, but in space there is no water. So as long as you can make sure that on Earth it's not going to corrode, so you keep it in clean room conditions, you keep it in a constant temperature with very low humidity, the corrosion is not such a problem. Because again, in space there's no water. The smoothness. The smoothness is not necessarily a disadvantage. Actually, some mirrors are made out of metals because it's so smooth that it reflects light very easily. So yeah, there are several mirrors. So you have one mirror here and then another mirror here, bigger. So the light comes to this one and it reflects to this one and it's collimated. So the smoothness is actually good. It's not a disadvantage. The shininess is similar, but actually the disadvantage is the capacity to transfer hot or cold, heat or cold very fast. Again, yeah, it's a disadvantage if you want to have the satellite in the structural way. So as you can see, they have different properties and you need to see which property you use for which part of the satellite. Sometimes, I really need to transfer heat and cold very fast. So I'm going to use a metal. But I am afraid that it's going to corrode. So I'm not going to use it in this part of the spacecraft, for example. So materials are very important. That's my whole conclusion. So, yeah, we're back. So we have to ensure, as I said, that all the materials that we fly to space are fit for the mission. Whether this mission is towards the sun, like BepiColombo, well, it was towards Mercury, but Mercury is very close to the sun, where it's very warm. Towards Jupiter, that is cold, like JUICE, or closer to home, like orbiting around the Earth. Each of these environments is different. It's not only the temperatures, it's also the radiation of the sun, several other aspects. So we have to make sure that we put every material that is suitable for that specific mission. How do we do that? We test them, of course, because we are the range of materials is huge. So we need to test all the coatings, glues, lubricants, metals. Each of them has its own objective. So we have to test all of them. So we test them by several techniques. This is only just 3 examples. We take microscopic pictures whenever there's a failure. And this, I think this is related to the question of CSI, of crime investigations. Sometimes a failure is like a crime investigation because a whole satellite before it launches, it's tested on ground. So sometimes it fails, and you want to know why it fails. Does it fail because the material is not good enough, because it was not applied properly, because someone handled it wrongly? So we take pictures, we test, for example, the fracture toughness, where we see when it breaks, with how much force it breaks. We do chemical analysis, we do several techniques. So here I want to show you a video. I'm going to show you two. The first one is of Aeolus, which is measuring the wind in Earth, and the effect of the very small atom particles, which are oxygen. So how did we prepare for Aeolus? So Aeolus is a European mission designed to measure the Earth's wind profiles. It orbits in low Earth orbit, where there is still a thin atmosphere from our atmosphere. It's still degrading. The ultraviolet radiation from the sun splits the oxygen molecules into oxygen atoms. These oxygen atoms can damage the spacecrafts because they can interact with ceramic and metals in a process called atomic oxygen erosion. So we need to account for that. We created an ATOX lab, which is uniquely qualified to measure the effects of ATOX. We tested a carbon-containing material that is used for thermal control. So first, we weighted the samples before and after the test, and we exposed them to the oxygen atoms, simulating orbit conditions. So we collected, after the exposure, the atoms originate in a laser plasma, and after the exposure, we collected some particles that had fallen in the plate during the oxygen atom radiation. So you could see them easily with UV light. They corresponded to the graphite yarns that were woven within the glass fibers and the Teflon. You could see that they had chipped off the cloth. You could see that they had been dislodged. There was a real risk that this could contaminate critical surface of the spacecraft. So basically they fell and they can stick on the lens, and then you don't see anything because you have your carbon there. So we saw it with a scanning electron microscope, and we visually confirmed that there was a material degradation. So thanks to this, the beta cloth material was improved, and then now Aeolus is happily measuring the winds on Earth and giving us very nice data. So basically what happened, as just to explain a bit, let it sink, is that the oxygen molecules are, so O2, these two together, are split into oxygen atoms, and here you have your sample, and these atoms erode your sample. And you can see this is a material that was coated to prevent this. This is the orange part. And then uncoated to see the effect of the oxygen atom erosion. And you could see with a microscope, you can see the valleys and the peaks. So it really made it like, like not nice, not smooth. And if you want to create your own model of Aeolus, you can go to esa.int/kits, and then you have how to download and build your own model of multiple spacecrafts. So that's one thing that we did, for example. Secondly, we tested also for BepiColombo. So Bepi is going to Mercury, it's super warm, so we need, again, to protect the spacecraft from the temperature. So we coated it. So it's the first European probe sent to Mercury. That's the division is awesome. And it will face extremely harsh conditions during the mission, again, because it goes to the coldness of space and then it goes very close to the sun. So large temperature gradients from -190 to 450, and strong radiation like UV, electrons, and protons. So we need to protect the spacecraft. So we built a dedicated facility here in ESTEC where we could expose the samples, the coatings, to ultraviolet and radiation particles and see how the coating deteriorated. We needed to assess the correct performance during the whole mission. We also had to test if the coating peeled off or unstuck. So we had to confirm that it would stay there after all the vibration tests. So coatings with several thicknesses were tested because we had to ensure, again, that they would not deteriorate, they would not crack, they would still protect the spacecraft on its way to Mercury. So, of course, we don't do this only in ESA. We have all our industrial partners, and we improve the performance of the antenna coating. And now Bepi is happily going to Mercury. It hasn't arrived yet, and it was launched in 2018.
In how many years is it going to arrive to Mercury? Sarah?
I think 8, 6.
Okay.
So yeah, so this is an example of the different samples. The top ones are shielded and the bottom ones are not shielded. And the blue arrow corresponds to the time that it would go on cruise, just like on the way to Mercury. And these last two, the ones that would be in orbit around Mercury, so close to the sun. So there are different temperatures. This was what is the different temperatures. I think this is called 100 coating, is that it remains white, because if it's, as you guys know, if it's white, it reflects the light, so the heat doesn't pass inside the spacecraft. So this black one is a no-go. So we had to go back with the industrial partners, improve the coating, let me test it again, improve it again, test it again, until we found a quite good white coating at the end of the test. And we could see here, there are some thermal images of how, this is another thing, is another coating, but how temperature is measured inside the vacuum chamber. So we have infrared cameras that tell us the temperature here is much warmer, much colder, and the blue is warmer, and so on. So these are just a couple of examples of what we do here in ESA as a materials and process engineer. And I think we leave the questions for after Jackie. Or
Yes, I think we can do a Q&A session at the end when Yaquelin is done with her presentation.
okay.
Can you hear me now?
Yes.
Yes.
Great. I had double mute. I hope it's not too noisy in this room. And I will share my screen. Give me a second. Let me know when you can see me.
We can see it.
Can you see me now?
Yes.
Yes.
Great. I cannot hear you very well, but I will just continue. So yeah, as Sarah gave us an introduction of what she's doing and how it looks, especially in the material side, I will follow up the presentation. I am working in the German Aerospace Center, who collaborates closely with ESA. So I will continue on the same path to explain you a little bit on how the test goes on my side, the mechanical side, and I will show you at a glance a little bit. I wanted to give you a quick overview. The DLR, at least the Institute of Planetary Research, where I work, we are maybe a little bit more than 121 employees at the moment. Publications and the scientist team have a rather busy task and elaborating and important for the school as well, the DLR lab schools that you can search another time. But it's a way to introduce DLR to schools to different levels of ages. And I totally recommend it. I was part of one trainee or activity down there, and it's really close to schools. So, you know, we are located in Berlin, and I put on the side a lot of images, mainly explaining that the wide branch of activities that DLR does. So this Institute for Planetary Research deals with the solar system research, and in particular the origin and formation of planets. We have a huge group of physicists where NASA was part of. Yeah, we study their moons, the planetary bodies, and by observation, as you can see on the spacecraft from the ground. Sorry for the noise, for the ground observatory. Yeah, we also have here lab samples, as you can see, in the LR in the spectroscopy laboratory, and we have also simulations, as you can see in the bottom image. So it's just one example of the different activities that we do at the LR. So I have a quick question for you at the beginning. So yeah, studying the solar system. Yeah, it's different techniques and different tools to be able to take satellites and space, as Sarah mentioned. So what do you think is more important, the remote sensing, the ground, the laboratory experiment, on the investigations and theoretical modeling? For that, we prepare in the 228888, so 4 8s, some pool to tell. Let me know if you can join. I will just give a couple of seconds. So yeah. Let me share. You can still see my screen, right? So yeah, it's not yeah, an easy question. It's not either one or the other. I think the important thing and the takeaway, it's the remote sensing and the ground laboratory and on-site investigations all works together. I cannot see if you are able to see the pool.
Yaquelin?
Yes.
Do you hear me? You need to go to Slido yourself and activate the question because we cannot see the poll yet.
Okay. Here you might be able to see.
There it is. Perfect. Thank you.
I can. Can you see? Can you see the pool? The pool answers?
Yes.
It's open. Oh, great. Yeah. Now it's quite slow on my side. Okay, we have one leading on-site investigations. Yeah, bringing going on site. So of course, laboratory experiments are very important. Sarah and myself will agree on that. Yeah, here it keeps changing. Yeah, we'll leave it until there. Yeah, my takeaway is the combination and the collaboration of all parts. So myself, it's involved. I'm involved in a small part of the whole muscles with aerospace engineering. And yeah, important is yeah, to have this huge collaboration and deep expertise. Yeah, in the institute, yeah, we do a little bit of all aspects. Yeah, and there is a huge effort and a lot of space engineers, women and men, working in spacecraft, satellites, landers, orbiters. And do you have any idea how many we have sent to space exploration, not observing only the Earth, but to space exploration? Any number will help. I will go back to Slido. Go back to the pool where I put some numbers. You can keep wondering how many you think. I put a set of 1 to 10 and the maximum plus 100. It's taking some time, sorry for that. Yeah, probably the question is whether our success launches or not. Yeah, there are a lot. Nobody says 1 to 10. For sure, we have done more than that.
Just
Here,
to ask, the question is for successful or for all of them?
no, I did not make the specification, but successful is my mean. But it's the information I found and I am tracking. Yeah, successfuls. Okay, most of you choose 100. So I found a interesting visual aid of pop chart one when you're doing visual aids, and here you can see some paths in an artistic way of how paths have been followed for the space. And actually, it's something close to 30 to 60. And here you can see some visual aids of all of them. And important here, I wanted to highlight that there are orbiters, landers, yeah, flyby options, flyby spacecraft, and all of them require yeah, the participation on the small part of the testing and laboratory. None of them goes without being tested and yeah, deeply understood, as Sarah mentioned at the beginning, from materials or from every aspect. Here I follow you. I wanted you to continue and thinking and how do we do it? How yeah, how these different variety of sizes and types, and yeah, it's important to have a overview and a clear understanding that it is a multidisciplinary activity, and yeah, we will never trying to understand everything from every aspect. Important the collaboration of all colleagues. And here I've put a little bit of on size wise to see how different each mission can be, from a small spacecraft to design spacesuits to either design a lander for different materials. As Sarah already mentioned, it's not the same coming close to the sun and going to cold icy moons in Jupiter. So it's very important. Here I put this is yeah, visual aid, because in the answer of how we do it is came to my mind, like and also in the path of my career, to understand how everything's combined and manage to have a spacecraft or a successful mission. Is undeniable, huge amount of work for every branch, in this case for every team, for every leaf, if you can see it. And for me was yeah, a way to remind that all branches yeah, are combining to yeah, the work. And in multidisciplinary team, huge collaboration, as I mentioned before, the scientist community, engineers as well, sometimes combined, sometimes with different path and expertise, and of course the rocket scientist. Here I put a tree, a branch example of how it looks. As I got introduced early on, I'm working also in writing a proposal for Envision, a mission that will fly to Venus. And this is where I got into the project management activities and technical requirements. And it's interesting how these branches develop. And once you have organized and clear, which is the path and expertise in each bullet and each yeah, line, a branch, as I keep mentioning, is where the multidisciplinary and collaboration plays a huge role. So just a takeaway of collaboration, which I don't miss a chance to always yeah, highlight. And here you can see different type of projects. So all teams might be different. Yeah, it's huge work, that's by default, but teams like ESA, they have expertise and heritage for different missions, and DLR as well, and many institutes that we have heard in these panels. So that was the important. And then I would like you to go to Lido again, if you don't mind, and then we can continue with our last question, which here you might need to type. Let's wait a second. Loading. So this question is related to the test facility. To here you go. It's taking some time. If you can see it, you can already answer. There were two questions. One is why people dress up in the labs. Very simple but interesting questions. It happened to me that I was already in school, elementary school, with 3 to 5 years old, and to look cool. Yes. Yeah, the clear probably answer contamination. Some yeah, interesting outcomes come from this question, because we dress up, we cover, depend on the level of cleanliness on the laboratory, and for that probably Sarah will have a huge overview if questions arise later. But yeah, we cover every aspect of humans, but yeah, for protection, for hygiene, yeah, it's in the same direction, but mainly because our body has so many particles and we contaminate easily the components. So either both sides, depending on what are we working on. Here, for example, there is no one is dressed up, so there is no clean room, no need for that. And this visual aid, these photos I wanted to show you, is a shaking facility. You have a shake table behind the window. Colleagues from the LR are there. We are making these tests. And on the left, you can find sensors. In a tiny, you can see in one of the tiny metal cubes a set, which is the axis where we are looking, and we are testing this metal component. We are making it shake literally. I have a small video here. Hopefully you can see. So yeah, vibration testing of the most common things in mechanical design. For almost everything that it's around us has been tested. Our chairs, our washing machines, everything in space. What makes our shake test very important is we need to survive the launch loads, which are the heaviest loads that our components will see. It can be the case that we are designing, we are working on a lander, and then the landing loads, and depending on the life of each component will be tested. This is one of the few footage I have handy to show you. And it lasts for hours, such a test, depending on of course, on the load. But it's very impressive how things that seems to be solid as metal, as Sarah mentioned, they can actually bend depending on the vibration. Sorry for the noise.
I'm
Yeah.
Yaquelin, we will
Yes.
need to start the Q&A soon,
Yeah,
because we are going to run out of time.
I'm over. I can also stop or make a quick close.
Yeah, just do a close.
Okay.
We'll have 1 or 2 more minutes.
Great. This is actually one of my final slides, which is the cleanup and dress up question that I made. So yeah, this is a ultrasonic bath in the left bottom part. So we shake and we put the vibration on some frequency, and depend on the solvent. We can use acetone as even water work, just for the vibration will take the parts away. And this is the slido that we just answered. And this is yeah, one of my final. If the noise is too loud for you, you can remove it. But it's a yeah, slow motion of the vibration of these waves, and a way to clean metals and plastics and ceramics as well. And this is yeah, in this following slide, I'm just closing my presentation. This is not a shaking table, but a sound laboratory that is an ESA facility. Myself, not been there. Probably Sarah has been there, but it's interesting that this also has to be tested in the sound. Yeah, this has to survive the shocks that the launcher will give to the spacecrafts. And I found myself, I found it fascinating as well. That is one of the branches that we need to take every spacecraft before launching them to a huge noisy room. And that's all from my side. Thank you. And then we can start with UA.
Perfect. Thank you very much. So we have a few questions. The first question, there's one that asks, have you ever seen an alien? It's, I think Sarah wanted to answer that one.
You are mute, Sarah?
Yes, sorry.
That happens.
No, yeah, that weird people, maybe aliens, well, the people that you might think, is this a person from Earth? But no real aliens, no. It's not
Neither
a
do I.
hoax.
Good.
You neither, no? It's not a hoax. Some people are like, oh, for sure, ESA, they have seen something and they don't say it. If we saw something, we would be the first one to say it because it's awesome, but we haven't.
Now, how does astronaut keep healthy while in the International Space Station?
I can collaborate on that. Yeah, healthy means well slept, well eat. So they eat enough, they exercise themselves, and they work not too much. So I think as every scientist around, that's always a challenge. But there, with no gravity, it's even like more tricky. So they eat superfoods. They sleep with an assisted bed. They have people and working a team behind them also to collaborating on the way the astronauts will live. So workload, food, diet, human interactions. There is a huge branch on space, human space, human psychology. So psychology for astronauts in few words. So it's complicated as in Earth.
And also they have bicycles and running treadmills in the ISS to make sure that they exercise, because otherwise their muscles atrophy and the bone density. So yeah, they have to do it. It's, yeah. If you don't like to exercise, don't be an astronaut.
Then there's one question that is more practical about how do you find your way around all those cables in your labs? Because in every picture there's thousands of cables.
Probably that's to me.
That's better for you, yeah, that's better for you.
That's not all the time, and whenever that happens, we always mark. It's tricky. I mean, you could have many sensors, especially I'm working just with components. I'm not like working with a huge satellite testing vibration, but I probably Sarah have seen it in ESA. But there are tons of cables, so you always keep a good track and well-organized work style with help for sure.
Good. And I think this one is a really, really good question, and I think it's important. Is what or who inspired you to become what you are? Like, what was your role model, if there's anything?
I will start because my answer is no one. It was basic. No, I did what I did just because I'm stubborn and I want to know things and I want to. Why? But that's it. No one. It's not that I was looking up to someone.
My case maybe similar. So I have maybe or maybe several names. Like I was also reading and I mean it's fascinating. I'm also a fan of science fiction. So actually books and writers and hard science fiction was always inspiring me. So yeah, I think I was just stubborn enough to go for it. As Sarah said.
And the final one, it says, we have a girl in our classroom that wants to be an astronomer and a boy that wants to be a space architect. Is it easy to pursue this?
Yes,
I would say so.
say yes.
Yeah.
It's always everything that this world, I think it's always hard work. but hard work can be enjoyable. I mean, if you see the purpose, you see the benefit, and then the effort is part of the joy. I don't think it's an easy job, but sure, yes, totally doable.
If you like
Sarah?
it's not hard. I mean, is it hard? Is it harder? Why is it harder to eat, I don't know, veggies for some people than ice cream? Because you don't like it. It's not because of the muscle. It's the same difficulty. So if you like it, it's not so hard because you think about it. Oh, why? So yeah, I totally recommend it. Yeah.
Great. If anybody wants to ask any question in Spanish now, because I think we have no more questions, at least that I see, in English. Well, if there's, oh wait, there's there's no more questions in the sense of like in, oh yes, it's fine. There's if there's anybody that wants to ask questions in Spanish, then we can go directly to Spanish.
There's one in Portuguese that says, if Earth is not flat. I will not even comment. No, it's not flat.
So if you want, we can.
One, the boy at the maths. That what can he do in relation with space?
Ah, yes. Sorry, I missed that one. True.
Yeah, actually, we have a lot of mathematicians working in ESA because, well, actually, Benji is a mathematician. So once I think, of course, you can be an engineer, but you can also be a physicist, a chemist, a mathematician, because you have the building blocks of everything. And then you just study maths and then you apply it to whatever.
And what kind of jobs can a mathematician do in planetary
From modeling,
modeling
the orbit, for example, modeling planets and modeling atmospheres. Ask NASA for that.
Also, if they go on the path of software, so application, there's also a lot of work to do on laboratory or on space application. So it's actually great to have a huge or a big base on mathematics. Yeah, well appreciated.
To the moon and we're going to build these calculations.
Okay, nice. Good. If anybody wants to write a question in Spanish, we can. Otherwise, I would start probably by asking the speakers if you could answer in Spanish. The questions. Okay. If you could answer, let's say, one of the questions. For example, the ones of like how can somebody become, or how did you, let's say, how did you decide to become a space engineer? But we answered that one in Spanish. Okay, so entonces la pregunta ahora en español es ¿cómo decidieron o qué las motivó a las dos personas que están presentando hoy, a las dos mujeres que están presentando hoy? ¿Qué las motivó para terminar convirtiéndose en ingenieras espaciales?
Yaquelin, ¿empiezas?
Sí. He explicado, he dicho que quizá un poco la ciencia ficción, que me gusta, tener cercano libros y poder pensar en lo que es posible en el espacio siempre ha sido una fascinación para mí. Y ha sido claro para mí que quería enfocarme en la ingeniería y la aplicación también fue muy clara. Estaba entre aviones y naves espaciales y fue muy sencillo. Y es así, ha sido un poco la inspiración en autores y ya.
En mi caso, bueno, primero perdón porque mi internet va un poco así, creo que Nikos está en otro meeting por ahí. En mi caso, sí, o por supuesto siempre estás mirando al espacio y qué habrá, qué guay, pero es más sí, la curiosidad y el ser un poco cabezota y el por qué, y esto cómo, y esto, y ya cuando empiezas a entender un poco el porqué de las pequeñas cosas, ya no puedes parar de preguntar por qué. Entonces, y ya no hace falta que preguntes por qué, sino que ya sabes más o menos, pues igual es por esto, y ahora ya el siguiente paso es confirmar, es por esto. Entonces es más la curiosidad y el cabezonerío, ser cabezota.
Ujú.
¿Y cuál es la parte que más disfrutan de su trabajo?
Yo puedo empezar un poco. Me encanta la multidisciplinaridad en la que estamos envueltas. Son equipos de muchas profesiones, de muchas variedades. Es una de las cosas que me encanta porque ya entre más sabes, más te das cuenta que menos sabes, ¿no? Hay tantas cosas y como dices, Sara, siempre tienes esa curiosidad del porqué y de investigar las cosas. Es una de las cosas que disfruto más, siempre estar aprendiendo, en especial si estás en la parte de ingeniería cercana a la ciencia, a los equipos que eligen, por ejemplo, qué objetos observar o para mí, sí, necesito decidir de qué material y diseñar algo físicamente, pero el saber detrás es una cosa fascinante. Entonces, para mí esa parte es lo que más disfruto.
Yo un poco también el trabajar en equipo, lo que es el trabajo del día a día, hay dos partes. Una es el laboratorio, que por supuesto es interesante porque te dan un material y otra vez, ¿va a funcionar el material en estas condiciones? Pues no sé, vamos a ver cómo diseñamos todo un experimento, a ver si ponemos esto aquí ya no funciona. Ese gustillo de, vamos a ver si lo conseguimos. Eso es por un lado, y por otro lado, la parte humana, que yo creo que ahora hablando un poco más de Women Engineers, la parte humana que yo creo que estamos bastante bien, sí, o sea, acostumbradas, sobre todo las chicas, yo creo, a intentar a intentar ser cordiales, a intentar no enfadarnos con nadie y tal. Entonces yo creo que como mujeres, yo creo que es el ver cómo interacciona la gente, intentar que todo funcione. A mí eso me parece también súper fascinante, el intentar que tú estás diciendo una cosa y tú estás diciendo otra, pero estáis diciendo lo mismo, solo que no os estáis escuchando o estáis hablando otro idioma. Eso a mí me encanta.
Sí.
Sí, creo que es un punto importante también para la vida. Lo que para mí, lo que saco del mensaje que dijeron ambas fue un poco también en la vida entender la colaboración como una comunicación constante, con gente que tal vez piensa distinto, con gente que ve el mismo problema desde otro ángulo, y intentar tal vez escuchar y entender. Así que bueno, por ahora no tenemos más preguntas, así que voy a cerrar. So I will just close now in English as well. I would like to thank you very much in the name of Lecturers Without Borders, in the name of Europlanet Society, and of all the collaborators of this event, and all the schools that are participating here. Some of them are already thanking us in the chat. And thank you very much also to the schools for participating in this event, and in all the previous ones, people that participated in the previous ones, the ones that followed us live through YouTube. I would like to thank you all, because without you, this would never have happened. So thank you very, very, very much. And I would like, I don't know if Nasia, do you want to say anything?
Well, I mean, that's I cannot say anything more because you covered almost everything. So one of the things I see here is that the schools want to actually thank us by voice. So they're asking if they can say thank you from the microphone. Should we? Yes? Should we say yes? Teacher number 3 in Greece, yes, this is a confirmation. If you would like to, the kids are ready to say anything they want to us. I think I heard two. And I also see more thank yous from the students. Everything you see with numbers and the name, this is students. They're not trolls, so don't be afraid. So thank you for taking time from your lab. We got that. We got that. Te ευχαριστούμε. Gracias, no? Gracias in español.
Yes.
Okay, so here we close this live series, and I want to thank everyone again from the organization. Great job, guys.
Thank you.
Bye.
Ciao.